All right, hello everyone. Welcome to our next lesson on complex numbers. This one, we're going to be taking a look at just some simple operations with complex numbers, adding, subtracting, and multiplying. Unfortunately, though, not division. We'll do that one in the future. Division of complex numbers can get a little bit interesting, but before we can handle that, let's take a look at some of the more basic operations. Okay, so let's start off with a little bit of a warm-up here, finding the value of these expressions. Okay, these are called telescoping sums because they involve terms that cancel out. For example, 2 minus 2 plus 20 minus 20 plus 200 minus 200. You know what that is? That's an easy one, right? They'll cancel out. They leave you with 0. What about the next one? I see a 100, I see a minus 100, I see 50. Okay, looks like this one's also 0. And 3 plus 2 plus 1, minus 1 minus 2 minus 3. Clearly, that one's also going to be 0 as well. Okay, how about this one? 1 plus 2 plus 4 plus 8 plus 16 plus 32 minus 16, 8, 4, 2, 1. The answer is not 0. Aha, 32. Because the 32 is the only term that doesn't cancel out. Okay, a little bit of a brain warm up there. So now let's look at a continuation of some of the talk that we had during our last unit. Remember that um, the whole idea behind complex numbers is the the act of creating a number, this kind of artificial number, and then checking to see if the math works. So mathematicians hundreds of years ago came up with the idea of the square root of -1. We called it I, referencing that this was not a real number, but let's give it a variable, and then from that, let's see if all the math that we would normally use with regular numbers, would they work with unique values like this? This is not something that we can hold or physically represent, but does the math work? And if the math works, can we then find possibly some use for the structure of it? Okay, so we looked at first the idea of how to represent a complex number as something that is based off of the real system, right? And like we defined the square root of -1 equals I. And then we defined, from there, we defined other negative numbers, right? So like if we had, say, the square root of -3, we represent that as I times the root positive 3. Now, from here, we can do math with the square root of 3. The I is just the imaginary part, but we can treat that kind of like a variable. That was the big idea that we picked up last time, was that by writing it in a form that is partially real, then we can do math with the real part that we already know how to do. That was kind of the way that we went around developing the tools to work with these special kinds of numbers. Okay, so now let's take a look at the coordinate grid. You might recall we have this particular coordinate grid here. So just a bit about this. The complex grid is unique in such that each one of these, it looks like it represents an ordered pair, right? But it's actually its own unique number. So for example, here's your real number line. We sometimes abbreviate that in math with as RE. So the real part is just along this line here. So the number 2, 3, 4, 5, or -2, -3, they're all along this axis here. And once you go outside the axis, that's when you start getting these imaginary parts. And the complex number 2 plus 3i is located, you go 2 on the real axis, and then 3 on the imaginary axis. So it's like going to the point 2 comma 3 on a regular grid, but what it represents is the fact that we're going off the real line. And we're going to treat this as if it were one number. It's one number with two parts to it, an imaginary and a real part. Um, so that each one of these, places on here represents a particular complex number. If you had a number that was along here, like this number here would be 1, 2, 3, 4, 5, like 6i, or negative 1i, negative 2i, negative 3i. Okay? And then a number down here would be like negative 2 minus 4i would be down here. Okay? So situations like that, we can then use to represent these numbers, again, in a more physical sense. And that's really what we're trying to go with here, is how can these purportedly imaginary numbers be represented in a physical state? So once we got over that hurdle, now mathematicians have to figure out whether or not the math actually works. So let's start at the basics. Addition. Our question is, does addition of complex numbers works? Like, can I take I plus I? Can I add that together? Now, what is x plus x? 2x, right? Does that work if the number isn't real? Like if you have I plus I? That was mathematicians' first question. And it seems kind of obvious that the answer is probably. I mean, if I have whatever thing that I have, if I have one thing and I put it together, I get two things. It seems obvious, but mathematicians had to check to make sure. So let's start with the dot, 2 plus 3i, right? And then now we have this next complex number of negative 8 minus 8i. So what does that represent? Well, that represents, maybe we're going to represent that as motion, right? So maybe we're going to see negative 8 along the real axis. So what is negative 8? That's to the left 8. So we're going to go left 8. 1, 2, 3, 4, 5, 6, 7, 8. And then the minus 8i is we're going to move along the imaginary axis. And the imaginary axis, we're going to go down 8. So here's my minus 8i. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and what point do I end up at here? I end up at the point negative 6, 1, 2, 3, 4, 5, minus 5i. Okay. So once I end up at that point here, now the question then we figure out, if I take 2 plus 3i and I add negative 8 minus 8i, what happens if I combine the like terms? I get negative 2 minus 8 is negative 6, and then 3i plus negative 8i is minus 5i, which is exactly what I ended up with over here. So with that, mathematicians then deduce that addition and, by extension, subtraction work as advertised. They decide that, yes, we can add our like terms together and we end up in a place that we would normally expect. So this is just like how we would do this on a real line, right? Instead of starting at 2 and then moving 8 units to the left, now we're going to do both at the same time. We start at 2, move 8 units to the left, and then we start at 3i and move 8 units in the negative I direction. Make sense? Long story short, we can add like terms, and we can subtract like terms, and all that works. And that wouldn't have really been able to be proven in a rigorous fashion without having this grid to prove that the imaginary line works in a very similar fashion as to the real line. So with that in mind, we could just try a few together, right? And just making sure that we see that all we really have to do is combine like terms. So negative 3. So for the first one here, we're adding two complex numbers. Just add the real parts together, add the imaginary parts together. Remember that, you know, when you combine like terms, the variable doesn't change. Same thing happens with I. For the next one, negative 37 plus 11, 26. Negative 26. 45 plus 81. Ooh. 40, 36? 36. Oh, and it's going to be, yeah, it'll be a positive 36. Okay, subtraction. Now, when we do this with polynomials, you might remember that like I sometimes you could distribute the minus sign. Yeah, that all works here. So you can do negative 3 minus 4, and that's negative 7. And then you can do negative 2i plus positive 5i to get 7i. All that works just lovely. Same thing with subtraction. Negative 37 minus 11, negative 48. Negative 45 minus 81, you get an even bigger negative, minus 126i. Okay? No issues there. We're going to treat it just like we treat a variable. Multiplication, though. Let's see if multiplication works the same way. Now, hang on. You might be thinking to yourself, isn't multiplication just repetitive addition? Yes. Well, in that case, if I add something n times, it's the same as multiplying by n. Yes. So if multiplication is just a bunch of addition, then multiplication should work, right? Yes, but. And what happens if we try multiplying by 2i? How do you multiply something or how do you add something an I number of times? Would I have to multiply by 2i? What would it mean to add something 2i times? Ooh, okay. See? A little bit of an issue. So let's see what we come up with. All right. So write the following in the form a plus bi. Okay. Now 2i is already in that form, isn't it? Because we have just, you know, you could say it's 0 plus 2i if you want, but we really generally don't do that. The 0 just lets us know that we're going to be along the imaginary axis. So 2i is right here. How about 2i squared? Well, 2i squared is, you can distribute the square, that becomes 4i squared. Now, this is where difference comes into play that you don't do with normal variables. Remember that there's a rule that says that I squared is equal to negative 1. Because of that, because I is the square root of negative 1, when you square both sides, you get a negative 1. Because of that, you get an answer here of negative 4, because you get 4 times negative 1. So we're going to plot that here. What about 2i to the third power? Well, let's see. You get 8i to the third, because you can distribute the power. Now, you might remember, what about I to the third? What happens there? Well, you can break this down as 8 times I squared times I. That's a negative 1, so this becomes negative 8i. Huh. Then what about this one? You've got 2i to the fourth power. So you're going to have, let's see, 16i to the fourth. But that's just 16 times I squared times I squared. So you get 16 times negative 1 times negative 1, which is equal to 16. And guess what you get? You get this pretty spiral. So here's a crazy assertion for you. It turns out that the exponential function on the complex plane forms a spiral. How fun is that? This is one of the unexpected results that happen with complex numbers because of that one single identity, that I squared equals negative 1. It forces these numbers to kind of behave differently as real numbers do. But that was part of the cool part of figuring all this out, is what do these numbers do and how do they behave? And here's a great example. They form a spiral. Okay. All right. So with that in mind, let us figure out um, a little bit more about how multiplication works. So, 4i times 3i. Remember, start by thinking that I is a variable. This would be 12i squared. But remember that I squared is equal to negative 1, right? So what is this equal to? Negative 12. I squared acts as a sign change. And that's a great way of thinking about it. I squared causes a sign change. So that now here you'd have negative 12i squared, but the I squared causes a sign change, it becomes positive 12. You get where we're going here? Because negative 12 times negative 1 is positive 12. So what's going to happen here? You get positive 10. Negative times negative is positive. But the I squared forces it to change to negative 10 again. How about negative 5 times positive 5? Well, that's negative 25i squared. But I squared forces a sign change to positive 25. And how about this one? Well, let's see. That becomes 25 positive I squared or negative 25. That's one of the unique cases that happens with I, is that I squared simplifies out as a negative 1. Because of that, all math and all complex operations that we can do with I always simplify down to a linear I or a real number. Now, which is actually pretty convenient. That way we only have the one standard form of A plus BI. Okay, so just some more multiply, right? So again, just kind of go through and we can figure out what each one of these is, right? Just remember, the I gets exchanged for negative 1 only when it's squared. So for the first one, you just get 35i. There's only a single I. How about here? At this point, you might be able to just kind of rattle that off and say, hey, you get a 35, you get an I squared, so that's just going to be negative 35. This is going to force a negative 1, so this is just going to be negative 3. 3 squared is 9. You get negative 9. When you have an I to the third, you get the negative 1 out of it, but you have an extra I left over. because it becomes I squared times I. So that turns to negative 1, but there's still an I left over. So you get negative 8I. Same thing here. You get I squared and I squared. You get two pairs of the I squared. They cancel out the negatives, turns positive. Ooh, negative I squared. Well, I squared is negative 1. Be careful, the negative sign is outside the I squared, so that applies after. You get 1. Let's make that clear, that you get an answer of 1. Okay, how about this one? Now it's the negative squared, so negative I times negative I is positive I squared, which equals negative 1. So see the difference? Okay, and if you like that, what if now we multiply two complex numbers together? How would this work? Well, now that we know that addition works, we know that multiplication works, we know that um, we can always multiply by a real number. Now we know what it's like to multiply by by an imaginary number. So we can now perform distribution, and distribution will also work. Again, treat I like a variable, except now, again, you've got a rule. I squared gets replaced by a negative 1. So that's going to force this to turn into a negative 45. But remember, we always like to write the real part first. For the same reason that, like, we locate that as the x-axis on our complex graph. So because of that I squared rule, and it flips that from real to from imaginary to real, you get some results that might be a little bit unusual or unexpected. Like this one. Let's write it out. Minus 40 plus 24I minus 5I plus 3I squared. Okay, no problem there. Now here's the thing, we're going to combine alike terms, but before we do, this is going to become a minus 3 because the I squared causes a sign change. So now we get negative 43 plus 19I, where the 43 might not have been immediately evident that that was going to happen, but it certainly does. Okay, let's try this one. So 3i plus 3 plus 2i squared. So 3 plus 2i times 3 plus 2i. You get a 9. You get a 6i. You get another 6i. And you get 4i squared. Okay, that I squared, you know the drill by now, becomes minus 4. Combine your like terms. You get a 5 plus 12i. Now, you might wonder, hey, 3 plus 2 is 5. That's a coincidence, actually. But it's not always completely clear that you're going to get a 5 there, which is kind of neat that this happens. Let's try the next one. 3 plus 2i, 3 minus 2i. Well, let's see. You get 9 plus 6i minus 6i. Uh-oh. 2i minus 2i, so minus 4i squared. Again, we multiply. Be careful. That is a multiply. So what happens? The 6i, the minus 6i, They cancel out. The minus 4i squared, again, that I squared forces this to change sign. So that becomes a plus 4. Your answer is 13. A real 13. Not an imaginary number. But you get a real number. Now, you might have predicted that might happen because you had a positive 2i combined with a minus 2i. But boy, imagine that. You multiply two complex numbers and you get a real value of 13. Wait a second, is 13 prime? 13 is only supposed to be 1 times 13. And did we just break the definition of prime? Not really, because the definition of prime, there's only two real numbers that multiply to give you 13, and that's 1 and 13. We can update that now. So complex numbers kind of get around some of those number rules that we've used for years. It can be a little annoying, but that's because it's a special kind of number. And that property actually gets used quite a bit and allows us to do some math that we wouldn't normally otherwise do. So more on that later. But yes, when you have two numbers like this, that when you multiply them and they come up with a real number, we call them complex conjugates. Because they're the same, they've got the same real and imaginary parts, but the imaginary parts are opposite sign, which causes them to cancel out when you multiply. And you're just left with a real value. So this is an interesting scenario that pops up every now and then. Okay, next task. What happens with powers of I? So we've talked a little bit about some of them, right? Okay, let's start at the beginning. We know that I to the first is I, right? We know that I squared is -1. I to the third, we know that one. It's I squared times I, so -I. And the I to the fourth was I squared times I squared is 1. We knew those from our work earlier. What about I to the 0? What's that going to be? So our rule that we used with 0 was that anything to the 0 power is 1. Right? That rule should exist here as well. Okay. Now here's the thing. Notice that I to the fourth is equal to 1. So it's like 4 i's can be kind of disappear. So what is I to the fifth? I to the fifth is I to the fourth times I, which is just I, because you get 1 times I. Then what's I to the sixth? It's I to the fourth times I squared. So it's going to have the same value as I squared. I to the seventh should have the same value as I to the third. I to the eighth would then have the same value as I to the fourth. And you get what's now known as the cycle of I. I, -1, -I, 1. And it turns out they go like that in a cycle. So when looking at higher powers of I, what you want to do is you want to realize one thing in particular. I to a power that's a multiple of 4 is going to be 1. Once you know that, you can then count where on the circle that you are. Okay? So let's take a look at a few of them and see what we can figure out. So let's look at I to the 10th, right? So I to the 10th, right? So we know that I to the fourth is equal to 1. Then you get I to the fifth I to the 6, 7, 8, 9, 10. I to the 10th is negative 1. So it's like you can count around the circle. How about I to the 17th? Well, we know I to the 10th is negative 1, so we'll just keep going. 11, 12, 13, 14, 15, 16, 17. Now, going from here, you may not want to start counting around the circle a bunch of times, right? So instead, what's helpful to know is what baseline value do you know? And an easy one to remember is that I to a multiple of 4 is equal to 1. So I to the 36th power. Well, 36 is 9 times 4. This is a multiple of 4. Automatically, we know that's equal to 1. So I repeats on a cycle of 4 instead of, say, negative 1 raised to these powers, which repeats on a cycle of 2. Okay, how about 45? Well, 45. Well, I don't know that, but I happen to know that 44 is a power of 4, right? So I to the 44th must be equal to 1. And if that's true, that means this must be I. And that's how we look at, powers of I. By trying to figure out where on the cycle a value that we can recognize is. One thing to remember, I to an even power is either going to be 1 or negative 1, and then I to an odd power is going to equal I or negative I, because I cancels itself out in pairs. All right. And there we go. So that's a little bit about addition, subtraction, and multiply. And we did some work with some powers of I as well, which just involves following a cycle. Um, so with that, mathematicians proved that complex numbers have arithmetic the same as real numbers do, and there's a lot of things that we can then do with them. All right. So hope this was enjoyable. Take care, and best of luck to you. Have fun.